Okay, welcome everyone. So Rachel Neville from the University of Arizona will give her talk today, and the title is Topological Techniques for Characterizing Ion Bombardment Systems.
Thank you, Sarah. And thank you, Sarah and Henry, for the invitation. Okay, I'm going to start just with a little motivation. So bombarding a surface with energetic ions, that really just means shooting ions at some maybe thin film of a material, is a common technique in kind of industrial technique or industry to smooth surfaces or to roughen them or to clean them. This process is called ion erosion or sputtering. And sometimes it makes a smooth surface, and under certain conditions, for certain materials, we end up with really nice, complex spatio-temporal patterns. So we can see here several examples from the Ion Bombardment Center in Germany. We have, this is experimental data. You can kind of see the scale on the bottom left here. So this is nanoscale features. We have kind of this maybe disordered hexagonal array of dots. And we get ripple patterns, this checkerboard pattern. And this is to varying degrees of order and defects. So this is interesting because it could be a nice single-step process for manufacturing nanostructures. Often this can be a complicated process, and so having this nice reproducible step or single-step process would be really nice. But to do this reliably, we need to understand the systems. So that's what I'm going to be focusing on in my talk. And something to, as we're honing in on understanding the systems, really what that means is we want to characterize the patterns and quantify defects to a perfect pattern, because ultimately the goal is to create very regular structures, regular nanostructures. So we're really going to hone in on order and defects. And my main argument is that topological techniques are powerful for quantifying this order, characterizing the structure, and kind of probing these types of systems. Okay, so in this talk, I'm going to zoom in on two specific systems, two different patterns that form. One is a checkerboard pattern that comes from kind of a crystalline semiconductor. So I'll look at the mechanism and the model, and then hone in on the topological techniques that we use to characterize the structure in that pattern. And then we'll look at hexagonal arrays of nanodots. This is from a binary semiconductor. Again, we'll look at the mechanism and model, and this time there's kind of two different questions that we can ask. So one is to quantify order, and another is to learn the parameters of the model. So we're going to use two different topological techniques to answer these questions. So that's where we're headed. And I'm going to start with the ion bombardment of an elemental crystalline semiconductor. So this is a single element. In this case, we're going to think about germanium. And that's just because it's one of the first elements to display this checkerboard pattern in the laboratory setting. Okay, so we have a thin film of germanium. It has a crystalline structure. It's a semiconductor at elevated temperatures. We're going to hold this sample at an elevated temperature above the recrystallization structure or temperature. And at this higher temperature, we get this checkerboard pattern that emerges. And so let's talk about some of the mechanisms that cause this pattern to emerge. So if we're bombarding a surface with ions, we're going to use noble gas ions, often argon. So the ions aren't going to react with the elements in the surface. It's just going to hit the surface, transfer energy, and then atoms are going to be sputtered off. So we have the surface kind of our system is decreasing over time. And there's several other mechanisms at play that makes this actually interesting. So the flat surface is unstable, and so any small perturbation or noise can lead to the spontaneous emergence of patterns, and these patterns will either continue or kind of smooth out depending on the conditions. So one of the things at play here is curvature-dependent sputter yield. So you can imagine if an ion hits the surface and you have some sort of topography to your surface and peaks and troughs, if it hits in a trough, more of the power is going to be transferred at the bottom of this trough. And so ions or elements are more likely to fly off in a trough than when an ion hits the peak. Less energy is transferred, and so your atoms are less likely to fly off. And so what this really means is that troughs will deepen, and it's not that peaks will grow, but peaks will deplete less quickly than the troughs. So you end up with troughs deepening and these peaks kind of persisting.
And Rachel, is a way to think about it just like if I hit the trough, in the trough I sort of have more neighbors they could bounce off? More neighbors?
Right, you can kind of see it in the area here. So this is maybe the area where power is transferred. So there's more, more area for the power to be transferred just because of the geometry of being in a trough.
Okay, thanks.
Yep. Some other things that play here. So when an ion hits the surface, there's atoms on the surface. This can cause the atoms on the surface to move around. So we have some momentum transfer from the ion bombardment. And then a big deal here is the Earle-Weibull barrier. So what this means is it's a nonlinear surface current. And you should think about it as a potential barrier. So when you have structures on your surface with maybe edges or kinks or bends in them, so a terrace type structure, it's difficult for ions to move across this terrace structure. And so this creates a little bit of a potential barrier. And so it really drives the direction that the atoms on the surface are moving and diffusing because of the structure. So in this case, we have a crystalline structure. And so we do, in fact, have kind of this terrace steps across the surface of our film. And when the temperature is high enough that we're above the recrystallization temperature, but not so high that we've amorphized the whole solid, then this Ehrlich-Weibull barrier really is driving the anisotropy of the system and having a big effect on the currents on this of the atoms on the surface of this system. Okay, and you can think about this if you have corners, your atoms aren't going to want to go over corners. They're going to want to go up surfaces that are flat, and so this actually creates an uphill current. Okay, so those are the mechanisms, but I think it's interesting to see what's going on. So this is a simulation of this process, and so we can kind of see the competing mechanisms in certain regimes will resolve to this really interesting checkerboard pattern. So here the color is the surface height, and so I kind of have these almost pyramidal structures and anti-pyramidal structures. So the dark is kind of these pits, and the light part is these mounds. And we'd like to better understand the interplay between all of these mechanisms and really to quantify characteristics that are observed in this structure. So, so this is interesting because first it was observed in a laboratory, Xin Yu, at the Ion Center in in Germany, observed this experimentally and then wrote down a model for what was observed.
Rachel, a question about that last picture. Yeah. Like, what's the size of an atom roughly in that picture? Like,
so here's kind of a similar pattern, and here's the scale across the bottom. So an atom is still pretty small in comparison to the patterns that are emerging, but these really are still nanostructures.
But so you have this checkerboard pattern, but still the atoms might have like some hexagonal regions of structure within that checkerboard pattern. Like,
right. So we're going to think like a little bit bigger than the atom.
Got it.
Yeah. Yep.
Cool.
Great. Thank you. Okay, so here's the model. So I just want to briefly mention everything that's encoded here. So we have the curvature-dependent sputter yield, we have surface diffusion, the nonlinear current, and the Weibull surface current. So the parameters here aren't perfectly tied to physical quantities, but they're, for example, kappa is affected by the temperature. Sigma is affected by the angle of incidence, so that's the angle that the ions are hitting the surface. This can be anywhere from normal, so that's at a 90-degree angle, but the angle can widely vary, and that affects the pattern. And delta is affected by the crystalline structure, so this is really driven, in this case, by the material that we're using. So we're going to focus in on sigma, and that's because Xin-Yu noticed in several experimental runs this phenomena where the surface, he said, is dominated by pyramids for positive values of sigma and inverted pyramids for negative values of sigma. So we'd like to measure this and quantify this. And I just want to kind of show you a little bit of what he means. So here's an example. Here's sigma equals 0. This is where we have up-down symmetry, and so we don't expect the mounds or the pits to either dominate. So we have early time on the top row, a later time on the bottom row, so we can see the pattern emerges and then slowly coarsens. And we have a negative value of sigma over here and a positive value of sigma over here. And it's a little bit hard to tell, but you can see that there's a difference kind of in the structures between sigma equals -4 and sigma equals 4, for example. Maybe we can see it a little bit more clearly here. So this is the surface plotted. I have sigma equals -5 on the left and sigma equals 5 on the right. And I've plotted it right side up and upside down. So if you look at this carefully, I think this is what the physicists are picking up on when they're observing this in their lab, is that the peaks are more well-formed for sigma equals +5, and the valleys are more well-formed. There's a clearer pattern for sigma equals -5. So this is what we're trying to quantify and pick up on. Okay, and we're going to do that with topological techniques. So what we're going to use is a sub-level set filtration. We're going to construct a cubical complex and track the changes and encode it in a persistence diagram. So we pick a threshold and build a cubical complex and raise the threshold and track our homological features through this filtration. This gives us a summary of the peaks and of these pits, if you will. Okay, so H0 measures the prominence of pits or inverted pyramids. So H0, remember, is connected components. So we can see that here. There's two kind of pits in this example, and we can see that they emerge. One is bigger than the other, and then they fill in. And so that's encoded with H0, and H1 will encode information about the peaks. Okay, but they do it in slightly different ways. We have to be careful here. We're using a cubical complex, not a simplicial complex. And so we have to be careful about connectivity to neighbors. So when we're building our cubical complex, we're connecting 4 neighbors. And that ends up being important because it means that the H1 and H0 are kind of measuring slightly different things. We also have a duality between H0 of my surface and H1 of my inverted surface. So I can think of this as H1 of the surface flipped upside down, or H1 of the super level set filtration, so taking all of the pieces of my function that are above a certain value. So this is the way we're going to get after encoding these types of features in the same way. So I really want to understand to make a fair comparison between these inverted pyramids and these pyramids. So we build a statistic using H0 of the inverted surface and H0 of my normal surface. Remember, H0 of my inverted surface is dual to H1. And this statistic will be, it encodes the average prominence of pits and peaks. And if it's positive, this indicates that the peaks will dominate. And if it's negative, this indicates that the pits dominate. So this is capturing exactly what the physicists are trying to capture in their experimental observations. So
and Rachel, when you say mean of the prominence is just like the length of an interval?
Yeah, it's a little bit loose here.
Okay.
So think of prominence as, so when we're looking here at the maybe well-formedness of these peaks, we notice that for well-formed systems, they're all approximately the same height. And so some of that's being captured in prominence. Yeah.
Thanks.
Okay, so to test this statistic and make sure it's capturing what we think it will, we ran a bunch of simulations at various values for sigma, fixing all other parameters. We started with initial conditions with white noise and allowed the system to evolve, and computed at each time step this statistic. And we have here just the plot over time and error bars over all of the trials. So some really nice things that we notice here. Sigma equals 0 has approximately a peak measure of 0 for the whole time. This is expected looking at the geometry of the problem. But this is useful to kind of validate the technique for use in experimental data. We notice that for positive sigma values, we end up with this positive statistic, and negative sigma values, we have this negative statistic. It's pretty well separated, so this could be a good indicator that this will be helpful to connect more fully the parameters of our problem to experimental data. And something else that's really nice here is that it seems that these statistics are fairly constant over the coarsening of the pattern. And that's actually nice because that's not something that we wanted to pick up in this measure. We know that the pattern coarsens, and so we don't want to be measuring the coarseness of the pattern. In this case, we want to be measuring the dominance of either the peak or the pits. Something else you can notice from this plot is that you have this big shift in early time. And what this really is telling you is from approximately time 5 to 25, what's happening is we're going from the linear regime in where the linear effects are really dominating the pattern formation to the nonlinear regime. And so we can really see where this shift takes place from this statistic. So that's wasn't expected, but kind of a nice side benefit of being able to see that here. So we can kind of understand when the pattern really emerges. So our collaborators in Germany have some experimental data, and so we're currently working with them to connect the experimental data to the statistic. And so that's kind of where this project is, but just this nice application of persistence, and it kind of captures exactly what you would hope that it would capture. Okay, the next example is ion bombardment of a binary compound. So the pattern that forms here is this near hexagonal array of nanodots. So before I get rolling too far on this one, this work is joint with Mark Bradley, Francis Mata, Daniel Pearson, Patrick Shipman. It's published in this paper here and supported by the NSF. So make sure I get that out there early. Okay, so same idea here. We have now a different solid that we're bombarding with ions, but we're still bombarding ions. Similar mechanisms are at play. So, for example, we have, again, we're sputtering ions off with by bombarding it with noble gas ions. We have curvature-dependent sputter yield. Here, because I have two species, think of my original solid as well mixed. So I have two different elements, for example, gallium and antimony. And in that example, antimony is preferentially sputtered, leaving the surface around 30% more often than gallium. And so, so you end up with a shift in your surface composition because one of your elements is more easily sputtered. So in this case, B is going to be more easily sputtered. Again, we have curvature-dependent sputter yield. So if an ion hits in a valley, more power is transferred, and so ions or atoms are more likely to fly off from valleys, and so troughs will deepen and peaks will kind of form. And we also have several different things happening on the surface here. Again, momentum transfer. So here, because we have two different species, there's going to be a downhill current, but one species is probably going to be, just because of atomic characteristics, ending up flowing more easily due to the transfer from the momentum of the ion. So, for example, here the red, which is species A, tends to flow downhill more quickly. We also have surface diffusion, which causes the downhill current of species B, and that's just kind of a smoothing mechanism that works actually against the curvature-dependent sputter yield and these other mechanisms. Okay, so we can write this down as a model. So we have U is the surface height, and crucial to this model is the fact that U and phi are coupled. So U is the surface height from a mean average. So we understand that the surface is being depleted as atoms are leaving, and so we take whatever the average surface height is as 0 for our model. So we're centering it on that. And phi is the surface composition. So if I have a binary solid and one species is preferentially sputtered, it's really important that my surface composition and my surface height are coupled. And so I can see the coupling here. We have curvature-dependent sputter yield, again, surface diffusion. Here's the preferential sputtering. And again, here in the second equation, we have momentum transfer and surface diffusion. So these are kind of all of the mechanisms that are at play, either causing the surface to eventually smooth out or causing patterns to spontaneously form and persist. So because my composition and my surface height are coupled, we're going to run all of our analysis with the surface height, but I have run it with the surface composition, and you end up with very similar results. The surface composition actually visually looks very similar to the surface height, so there's not a lot of lag there. So this is just an example of the formation of these patterns. So something I want you to kind of hone in on and notice here is the emergence and resolution of defects in the pattern. So we'll come back around and define that more precisely, but you can kind of see that peaks will emerge over here. It looks like a peak is slowly emerging, and this process does slow down as time goes on, but there's kind of this jostling that occurs, especially initially as the pattern is forming. Okay, so I really want to hone in on these defects in the pattern, because the hope is to understand this system well enough to use it for manufacturing these nice regular arrays, hexagonal arrays of nanodots. And as we have it here, this is an example that is fairly rife with defects. So you can see some areas of well-orderedness, but there are definitely some defects here. So let's talk about what those defects are. Defects can appear in a near hexagonal lattice in several different ways. So one of those is a grain boundary. So when two separate regions that are aligned in similar ways come together, so this blue region and this yellow region are aligned differently, they come together, and this grain boundary along which they come together has a bunch of defects to the pattern. So what's drawn behind here, so all of the dots, I should think of those as points in my lattice or nanodots. And I've drawn also the Delaunay triangulation and the Voronoi regions, just so that we can see a little bit more clearly the pattern here. So we have what are called pentahepta defects that are popping up all over the place. So in a perfect lattice, you expect every dot to have 6 neighbors. When there's defects, dots will have 5 neighbors and 7 neighbors. So that's our pentahepta defect. There's also perturbed or completely missing peaks. Those are possibilities as well. These are defects that we'd like to be able to characterize because we do in fact see them in our system. So here's my example of my system. I've pulled out the peak locations as a point cloud, drawn the Voronoi region over top just so that we can see these defects a little bit more clearly. So here's just several examples of pentahepta defects, but we've got something going on here. They're all over the place in this one. If you squint, maybe this is a grain boundary. So this region and this region are differently aligned, and somewhere along here they come together. You can also see, if you kind of squint and scoot back a little bit, other regions where these lattices are coming together. So if we want to quantify this order, let's talk about some of the tried and true methods that people tend to rely on in this field. So the first one is fairly standard, the spectral method. So if you take the Fourier transform of your surface, and then you radially average your Fourier transform and measure the width of the first order Fourier peak, this should give you a measure of order. If you have a perfect hexagonal lattice, you're going to end up with 6 very concentrated dots in your Fourier transform, all along this region, but very concentrated. And so the width of your first order Fourier peak is going to be very narrow. And as it broadens, that's an indicator that your pattern is more disordered. The challenge here is that sometimes your peaks aren't separable from the background, especially if you're working with real data or from each other. And also this lacks sensitivity to small defects or little changes in, for example, in grain boundaries where we have several well-ordered regions that are coming together. So this doesn't quite have the sensitivity that we're hoping for, and I'm going to circle back to this a little bit later just to give you an example of what I mean. Some other methods that have been tried, a geometric method. So if we're computing the correlation length, we really care about the region of exponential decay and the autocorrelation function. The challenge here is that in an ion bombardment system, somebody has shown, Bacher and al., that this measure can be stable even as the order increases. So what they mean by order here is they're kind of visually gauging order, but you can see what they mean. Here we have a well-ordered system, and here, even if I can't quantify it, I can say that this is less well-ordered. So that's out. So I've been drawing the Delaunay triangulation and the Voronoi regions on these examples. So what if we use those to measure order? So we can count the number of nearest neighbors, for example, or build a measure out of the edges in my Delaunay triangulation. So this does capture some of the defects that we're after. The challenge here is that I can perturb the center of this lattice point anywhere in this green star region, and the number of nearest neighbors doesn't change. So small perturbations of lattice points may go undetected, and so this measure is not really sensitive enough for what we're looking for, especially the nearest neighbor metric.
And maybe another way of saying that is if you're really close to that green region and then you cross it, like an epsilon change makes a discontinuous change in the measure as well.
Yes. Yep, it does. Yeah. Thank you. So we're going to use persistence in this circumstance as well. So just as our quick reminder, we're going to start with a point cloud. We're going to center an epsilon ball on each point and build a simplicial complex. As we increase the size of epsilon, we see kind of this topological structure emerge and then disappear, and we're going to encode that in a barcode or a persistence diagram. Now, when we're building the simplicial complex, here we're going to use the Vietoris-Rips complex, partially because it's very computable, but also because it's just so useful here. So here's just a little subsection of a perfect hexagonal lattice. I'm going to center balls at these points, and all of a sudden, everything simultaneously goes from being disconnected to fully connected if I have a perfect hexagonal lattice. So we're really going to use this fact here to build a statistic. So if I'm computing persistence using the Vietoris-Rips complex over a whole system, the variance in H0 should be 0. I should end up with a whole bunch of bars that are exactly the same length. So any variance in that is going to indicate some sort of defect. And I should end up with, in a perfect lattice, I'm going to have no H1 bars. And so anything in H1 is also an indicator of a defect. So we could do the sum of the bars in H1. I can do a linear combination of these two statistics. I chose these scale parameters just so that if we choose an edge length of 1 in our, so the distance between 2 nanodots is 1 in our hexagonal lattice, then this combination should range from 0 to 1. So you can take this technique, and not just for hexagonal lattices, but persistence gives you a clear indicator of a number of different lattice structures. If you scale everything so that the longest edge of your triangle is 1, you can write down exactly what you expect the persistence diagrams to look like, and so you can use persistence as kind of this measure of how far off you are. But here we're really focusing in on hexagonal lattices, and this really seems to be a well-suited measure for this. So here we can just see several defects. This is one example of a threshold value and the Vietoris-Rips complex associated. So we're missing a peak, and we have several perturbed points. And those appear as H1 bars, and they also appear as causing some variance in some of the H0 bars. Okay, so we can apply this to real data. So I have the peak locations, several different threshold values, and then all of this variance and all of this spread, all of this variance and all of this spread are indicators of defects in the system. Okay. So I didn't spend a whole lot of time digging into the model, but one of the challenges is that as we vary parameters, in particular, we're going to vary the parameter B, but the most linearly unstable wave number, K sub t, doesn't depend on B. So what this really means is that in some circumstances, the spacing of nearby nanodots is going to be affected by nonlinear effects, But what I'm really interested in this case, as a first pass, is honing in on linear effects.
Rachel, what was B again?
Sorry, yeah. B is a linear parameter, right, that's associated with momentum transfer.
Okay.
So if we're looking at the PDE, this is, as far as parameters go, this is a fairly friendly place to start in understanding the pattern. And part of that is because we know that as B changes, so B, you can think about it in the model as it encapsulates the interaction between this downhill current of species A, driven by momentum transfer, and also we have a downhill current of species B, and at some point there's kind of a balance between the two. So if B is large enough, my surface is, the flat surface is stable, but if B is small beneath some like critical threshold, and because the sputter yield of A is lower than B, the peaks will erode away, and A will accumulate in these kind of depressions. And so I have a pattern that really nicely forms. And so in dynamics, it's called a Turing bifurcation that happens with B. So we understand at least some of the dynamics that are happening with B. If I want to be able to apply this to data, I need to normalize, and so we're going to retain a fixed number of nanodots in a square and rescale it to fit the square. This is going to help us avoid the fact that we have a slight coarsening of the pattern over time. So that's what I'm saying up here, is that the dots are spaced a little bit further apart as time goes on just because of nonlinear effects. So that's not what we want to measure first. So this is important, especially if we want to focus in on data. Okay, so here's the experiment. We're going to fix parameters, all except for B. So we know that there's a Turing bifurcation at some critical threshold value of B. We're going to call that BT, and we're going to generate a bunch of examples near this threshold and a little bit further away from this threshold. So this is after my Turing bifurcation. So we do expect patterns to arise for B slightly less than this threshold. Above this threshold is where the patterns don't show up. And we would expect, just from the PDE, that hexagonal orders improved for B closer to the threshold. So what we see here is on the left, early time, and on the right, late time. We have very close to threshold and a little bit further away, close to threshold and further away. We're going to use persistence to quantify the order here. We can visually inspect this and say it seems at early time that my system is actually more well ordered for a farther away value. This is surprising looking at the system, but we'll get back to that. Okay, so I've computed this statistic over a bunch of different examples for a long time. So each of these time steps, we've computed the statistics, and here are the error bars. So the red is very close to threshold, blue is a little bit further away. We've just zoomed in on the second panel on all of these. And what we see here is that we actually, with the persistence measure, pick up the hexagonal order during the initial transient dynamic phase is much better for parameter values farther away from threshold than close to threshold. And this is actually not captured in the Fourier full width at half max. So this is capturing something that we notice by eye, but we haven't been able to quantify with our standard techniques. And so the thought here is that kind of a rapid commitment to a pattern. So we can see here that very early on, a pattern is kind of committed to, and then defects kind of have to slowly work their way out, if you will. That is actually hinders long-term order, this quick commitment. A slow commitment to to a pattern will actually allow the system to kind of more or less jostle into place, if you will, into a better ordered system. I think for the last few minutes, I'm going to talk about one more example of how persistence can be used in this example. So that's nice, but it really is honing in on a very specific question on characterizing order as it relates to a one parameter value. So this is nice. The previous method is nice because it does allow you to take data and quantify and compare degrees of order for these systems. But something else that we might be thinking about is taking the peak location might be smoothing out some information or losing some information. So if we're thinking about a sublevel set here, we can really see clearly there's some higher regions and low regions. And it's thought that these high and low regions are really due to the zero mode or the soft mode and nonlinear effects. So we'd like to understand kind of the variance in these regions a little bit more, ultimately learning parameter values. And that's because sometimes these low regions, the defect will form and continue, and then kind of catastrophically cause a large defect here. And other times the defect will form and then kind of resolve itself over time. And we'd like to really understand that process better. Okay, so again, we're going to vary the linear parameter, but this time I'm going to vary it from 0.9 to 0.99, so filling out my parameter space a little bit more. Our big goal is to train an algorithm to classify samples of this generated pattern at a moment in time for now by parameter, and we're going to use persistent homology to do that. Something else that we need here is once we have a persistence diagram that's encoding all of this structure, the structure is more rich, and so we want to be able to do something with that structure, so we're going to use persistence images. So persistence images, we take a persistence diagram, transform it into birth persistence coordinates at each point. We're going to center weighted Gaussian and then sum the whole thing up, overlay a grid, and integrate over the surface. So we end up with this nice vector representation of the persistence image that really or of the persistence diagram that encodes the important features here. So this is a stable representation, and one of the punchlines here is that it provides a wide access to machine learning tools. So the process here is we're going to run a bunch of simulations. We're going to compute persistent homology using a sublevel set filtration and cubical complexes again in this case. Then we're going to compute persistence images. Just as a note, experimentally this is robust for a wide range of parameter values. We're going to use some fairly standard choices here like a bump function, and then we're going to classify using machine learning techniques. So just some standard, in this case we used the subspace discriminant ensemble. Other methods yielded similar results. So just as kind of a visual example, if we're looking at the classification accuracy, we can see very clearly, okay, so H0 doesn't help us a ton in our classification. H1 really is capturing most of the information about the structure. And the interesting thing here is that the way that things are misclassified is that they're in adjacent, often they're in adjacent parameter values. This is really nice because it's promising. Our parameters were a fairly fine grid of parameter values. We used white noise initial conditions, and that causes a lot of variation in the surface and the defects. If we think about early and late time classification, we end up with reasonable classification and much better classification if we allow ourselves to look at neighboring classes. So we can also include in our classification several time steps just by concatenating persistence images taken at several steps. And this ends up being a really useful classifier. So we end up with surprisingly high accuracy for the problem, and if we look at how things are misclassified, we're actually getting close to the mark most of the time. So we can do this with nonlinear parameters. I'm going to skip through that, but kind of the same results. So the big picture here is that persistent homology and summaries of persistence diagrams can be used to effectively quantify order and symmetry in these ion bombarded systems. It can lead to some novel observations or different ways to quantify dynamics, especially things that practitioners are observing but not able to detect or quantify automatically. And ultimately, this can be helpful maybe even in learning parameter values, so connecting the model to experimental data. So future directions, our initial work on this has shown that that persistence can be useful for learning parameters, but there are a lot of parameters to vary, and so we're still working on building a model that can more robustly predict parameters. And also, I'm interested in working on including the temporal evolution of these structures. Right now, we're using snapshots of time evolution, and several examples in time tends to fill out the picture, but I think there's just a lot of fruitful work that can be done in this direction. So with that, I will end.
I guess now is the time to unmute yourself and clap for Rachel's talk. Okay, and now it's the time for questions. I'm actually going to start by asking, so Rachel, I can't see you right now. Okay, so with the classification to other state-of-the-art methods, or I mean,
yes.
because it's like because you just wrote like, you know, this is how much is classified correctly. I'm just wondering, like, if you compare it to other methods, like, you know, how does it do? Is it like really useful to include the H1 or?
Right. So for this system, there's not a lot of work that's been done on learning the parameters, and so there's some. We've compared it to some kind of naive classifications. For example, vectorizing using our whole surface as a feature vector, and trying to quantify the order in other ways. It depends on the method, but it's somewhere in the like 20s to 30% accuracy. So this is actually capturing a lot about the system. Yeah, that's a great question.
Rachel, in these parameter identification tasks on the hexagonal grids, would you say that the sublevel set persistence is more discriminative than finding the peaks and building Viator rips?
Right. So I didn't go into that, but it ends up being much more discriminative than just using the peak location. And the thought is that that really one of the big effects in the formation of the pattern and kind of the formation of the defects are these. They're called soft mode or large wave number effects, and so that's where you get like the low regions and the high regions, and so just the peak locations isn't really capturing the fullness of that, even if you use the peak locations in 3D.
Oh, and in 3D, meaning the height of each peak as well, but not the height.
Right. So you can put it as, you can take the peak location as a point in R3 instead of R2, but that doesn't quite encode enough about these high and low regions.
Right. It's still a lot less information than the surface height everywhere, which sublevel set takes into account.
Right.
I had one more question. So going back to your first segment, I asked this already, but you sort of described, or you defined this parameter as a 4-letter acronym like PHPM. Yeah. So this mean of H naught, this is an average of the prominence. And the prominence you haven't really like defined explicitly for us, but you told us roughly speaking what it is. Is that right?
Right. So, sorry, yeah. So, if we're taking like the mean of H0, what I'm meaning here is the average bar length.
Fantastic.
Sorry, that's not written. Yeah, sorry, that's not written very clearly, but
no, that was my guess. That was my guess.
Length, for H0 and average bar length for the flip surface. Yeah.
Right, and then PHPM is sort of like taking those into account to say whether the valleys or the peaks are more prominent. Okay.
Yeah.
Thank you. Fantastic.
Thanks.
Okay, so do we have any other questions? Yeah, sorry, I disappeared for a second there. My connection just dropped, so I'm not sure what happened there.
No worries.
Okay.
All right, I think
hi. Hello?
Oh, go ahead. Yeah, please.
Okay.
Please go
Sorry.
ahead.
So when you were doing the persistence images, when you were saying the class is plus or minus one, were you like you moved the mouse kind of along the kind of the middle axes, especially with the one on the right? Were you saying that the middle classes are the ones like kind of directly adjacent to this here? So
Right. So
like,
so anything along the diagonal is classified correctly. But for example, like there were 3 examples that I think were meant to be in this parameter category, but actually were classified in this parameter category. So one neighbor over, or if you're looking at our parameter values, that's a difference of 0.01 in our parameter value B.
okay, I see. Cheers.
So yeah, sorry, these are in order of parameter value, and so things close to the diagonal are actually close in parameter value as well.
Okay, awesome. Thank you.